Okay, so you might have come across the concept of multiplicity in an earlier segment when you were trying to prove the spectral decomposition theorem, but let's very quickly try to recall what the main idea is, right? So every eigenvalue has a multiplicity, and there are two ways to find multiplicity, right? One way is to do precisely what we did here, right? So you start from this definition and you just derive for each eigenvalue, you find out the eigenvectors corresponding to that eigenvalue, right? So in this case, we found out that there is only one eigenvector. So when I say there is one eigenvector, again, I just mean one linearly independent eigenvector. Okay, of course, by picking x1 to be arbitrary, you can get many, technically infinitely many eigenvectors, right? Okay. So there's only one eigenvector here, right? So that multiplicity is the number of linearly independent eigenvectors corresponding to lambda. Okay, the number of linearly independent eigenvectors corresponding to lambda, that we will call the geometric multiplicity of lambda. Okay, the geometric multiplicity of lambda is the number of linearly independent eigenvectors corresponding to lambda. Okay, very good. So in this case, for this matrix, so if you pick a equal to 0, 1, 0, 0 and lambda equal to 0, for this the geometric multiplicity happens to be 1. It is only one eigenvector corresponding to that, right? However, suppose you had come across, you had tried to do this a different way, meaning that let's say you found the characteristic polynomial of lambda. Okay, so now from here on, I'm going to use mu as a variable for the characteristic polynomial, not lambda. So I'll do det of mu I minus a. Okay, det of mu I minus a. Okay, so mu is a variable here. Okay, so if you find the characteristic polynomial of this matrix, you can very easily see that comes out to be mu square. Okay, so characteristic polynomial will be mu square. So if you look at the multiplicity, if you look at the roots of this characteristic polynomial, right? So you set mu square equal to 0. It's a degree 2 polynomial, right? So it's supposed to have two roots, correct? So mu square equal to 0 has root 0, right? You say repeated, right? Repeated, right? So the root 0 here instead repeats, right? So you say that 0 has multiplicity 2 here, right? That kind of multiplicity is called the geometric multiplicity. It's called the algebraic multiplicity, sorry. So the algebraic multiplicity of lambda is algebraic because it comes from the roots of the characteristic polynomial, correct? Algebraic multiplicity of lambda is the multiplicity of the root lambda in the characteristic polynomial det of mu I minus a. Okay, let's recall that for any polynomial, right, every polynomial has, you can write a polynomial like this, right? So as in terms of like mu minus lambda 1 to the k1, mu minus lambda 2 to the k2, like this, right? And mu minus lambda 3 to the k3 and so on, right? Then these quantities lambda 1, lambda 2, lambda 3 become the roots of the polynomial, and the corresponding multiplicity are the powers k1, k2, k3. Okay, so root lambda 1 repeats k1 times in some sense, root lambda 2 repeats k2 times. Okay, fine. So here these powers are called the algebraic multiplicities of lambda, right? So if a characteristic polynomial, for example, has something like mu minus 1 to the power of 10 and something else, then you know that the eigenvalue 1, okay, 1 is an eigenvalue, right? And the corresponding algebraic multiplicity is 10. Okay, however, the geometric multiplicity can be something different. Okay, for symmetric matrices, algebraic multiplicity will be equal to geometric multiplicity. Okay, for symmetric matrices, that's quite amazing, right? If you just write down this polynomial and you factorize it, and whatever power comes on top here, right, it tells you that there are also that many eigenvectors corresponding to the eigenvalue 1. Okay, so if you get mu minus 1 to the power of 10 and this matrix A happens to be symmetric, then you know that the eigenvalue 1 has 10 linearly independent, in fact orthogonal eigenvectors. Okay, that's quite amazing. I mean, that's the spectral decomposition theorem, the beauty of it, right? So in general, there is a result which I am not going to prove, which you might have seen before, I am not very sure, which says that the geometric multiplicity of any eigenvalue is at most its algebraic multiplicity. Okay, meaning that if 1 is an eigenvalue, let's say with algebraic multiplicity 10, as here, algebraic multiplicity is whatever power that comes in the characteristic polynomial. So 1 is an eigenvalue with algebraic multiplicity 10, then that means that the eigenvalue 1 will have 10 or maybe less than 10 eigenvectors, linearly independent eigenvectors. So it could have 10 eigenvectors as in the case of symmetric matrix, or maybe it could have 8 eigenvectors or 7 or 6 or whatever. It could even have 1 eigenvector. Okay, but in fact it will have at least 1. So it will have 1 less than or equal to geometric multiplicity less than or equal to algebra. It will have at least 1 because recall that if lambda is a root of this polynomial, that means let's say if determinant of lambda I minus a equal to 0, then ax equal to lambda x has at least one non-zero solution. Correct? Has at least one non-zero solution. Okay, this is because if a determinant of a matrix is 0, then there is at least one non-zero vector in the null space. Correct? That gives you the corresponding eigenvector. There will be at least one for sure, but they may not be as many as the polynomial demands in some sense. Okay, the polynomial has a much higher power, it may not have that many. That is what is happening here. For this matrix, if you see a equal to 0, 1, 0, 0, you see that lambda equal to 0 is the eigenvalue, and if you write down the algebraic multiplicity, that is 2, but the geometric multiplicity is only 1. Okay, there is a difference in the two things, right? This we will try to understand in slightly more detail, without many proofs actually in this lecture. We'll just try to understand. Okay. Of course, it is possible for a matrix to have many eigenvalues, and each of these eigenvalues having different multiplicities. Okay, for example, let us take this 3 cross 3 matrix. Okay, I'll construct this 3 cross 3 matrix by taking the 2 cross 2 block that we just discussed. Okay, and adding another, let's say 1 here. Okay, so something like this. Okay. So I'll use the 2 cross 2 block that we just discussed here, and I'll just add a 1 here. Okay, so it's like a block matrix construction. Okay, so let us see what are the eigenvalues of this matrix, right? So you can approach from the definition. Well, here it's very easy because it's again an upper triangular matrix. So you very immediately know that 0 and 1 are the eigenvalues, right? In fact, if you find the characteristic polynomial, you get mu square into mu minus 1. Okay, mu square into mu minus 1, that will be the characteristic polynomial, correct? So the eigenvalues are 0 and 1. Okay, but if you go by the polynomial, 0 seems to be repeated once, right? So 0 has multiplicity 2. So sometimes you'll see people writing like this: the eigenvalues are 0, 0, 1. Okay, but they are writing it from the polynomial perspective. Okay, so lambda equal to 0, lambda equal to 1 is an eigenvalue. The algebraic multiplicity of 0 is 2 and 1 is 1. Okay, because in the polynomial you have a power of 2 that's going here and a power of 1 that's going here. Okay, now let's look at the geometric multiplicities, right? So how many eigenvectors are there for eigenvalue 0? Okay, for that I have to multiply this with this matrix with x1, x2, x3 and set it to 0, correct? I have to find out how many eigenvectors are there for 0, and you can very easily do the computation here, and you will see that the only eigenvector is e1. Okay, just very easily multiply this and you will conclude that the only eigenvector is e1, right? In fact, there is only one eigenvector corresponding to lambda equal to 0. Okay, that is e1, like before. For lambda equal to 1, what is the eigenvector? If lambda is equal to 1, once again you can just multiply 0, 1, 0, 0, 0, 0, 0, 0, 1 multiplied with x1, x2, x3 is equal to x1, x2, x3. Okay, once again I leave the computation to you. And you will actually see here that the only eigenvector is e3. Okay, the only eigenvector for this is going to be e3. I'll leave this as an exercise. Okay, this is not. So you see that for this 2 cross 2 matrix, right, the algebraic and geometric multiplicities match for lambda equal to 1. Okay, but they don't match for lambda equal to 0. In fact, if the algebraic multiplicity is 1, it forces the geometric multiplicity also to be 1. See, because of this inequality chain here, right? If this guy is 1, this also forces to become 1. Okay. So here this has the same algebraic and geometric multiplicities, but here it's not so much, right? So here it's a 3 cross 3 matrix with 2 eigenvectors, only 2 eigenvectors. Okay, fine. So in general, there's another result which you might already be aware of. Let me just write it in because it sort of fits in this context, right? If matrix A, if the characteristic polynomial of the matrix A, let mu I minus A equal to 0, has n distinct roots, okay, meaning that, let us say, meaning that all roots have multiplicity 1, okay, all roots have multiplicity 1, okay, or no repeated roots, okay, no repeated roots, meaning that here all the algebraic multiplicities are 1, okay, fine. Then all the geometric multiplicities become 1, okay. Then A has n linearly independent eigenvectors, okay. Okay, so here I am assuming A is n cross n, okay. So if all the eigenvalues are distinct, you will be guaranteed a basis of eigenvectors that spans the space. You will get n linearly independent eigenvectors. But if some of the eigenvalues are repeated, that means they have in the characteristic polynomial, they appear with some powers, okay, in the factorization, then you may not have full set of eigenvectors, okay, fine. So this scenario is not limited to 2 cross 2, 3 cross 3 matrices. In fact, here I gave you an example of a 3 cross 3 matrix with 2 eigenvectors. No, you can actually also construct a 3 cross 3 matrix that has only 1 eigenvector. Okay, so let's actually look at a direct generalization of this 3 cross 3, this 2 cross 2 matrix, right? So this 2 cross 2 matrix is like this, right? 0 1 0 0. Let's just generalize it. Okay, meaning that we will take the following 3 cross 3 matrix. I'll take M to be 0 0 0. It's a 3 cross 3 matrix with zeros everywhere on the lower triangle and on the diagonal, and it has ones on just to the right of the diagonal. So it's like this, right? So this here is the diagonal of the matrix, right? And the thing that comes above it is called the super diagonal. Okay, so this thing is the super diagonal, and this is the diagonal. Okay, so basically this is a matrix that has ones on the super diagonal, right, and 0 everywhere else, right, mean diagonal and everywhere, right? So this is an upper triangular matrix by construction, right? Now why did we construct this matrix, right? Because if you look at the action of this matrix, meaning if you interpret this matrix as a system, it becomes very obvious why we picked this, right? So the input here is x1 x2 x3, then we try to find the output, right? So what happens when you multiply x1 x2 x3 with this matrix? You can see that once again, just like in the 2 cross 2 case, this x3 gets pushed up to the second coordinate. So you actually get x3 here. This x2 gets pushed up to the first coordinate. So x2 goes here, and this x1 gets thrown out. Okay, and the ending entry is just replaced with the 0. Okay, so this matrix M acts like a shift. Okay, so acts like a shift without any acts like a shift that simply ignores the overflow. Okay. So if you look at this matrix M, and then let us try to find the eigenvalues and eigenvectors of this matrix, right? Once again, if you try to find the characteristic polynomial, it is just mu cube, right? The eigenvalue is just 0, right? 0 is the only eigenvalue. 0 is the only eigenvalue, right? What are the eigenvectors, right? For you to get eigenvectors, I need to make this equal to 0, is it not? Okay, so for eigenvectors, I need m times the vector to be 0 times the vector, that's just 0, right? Now if you do see this, you'll see that x2 and x3 must both be 0, correct? So if this vector has to be 0, then x2, x3 has to be 0. That means x1 is the only free coordinate, correct? So any eigenvector is like x1 e1, any multiple of e1. Okay, and that means the only unit eigenvector in some sense is e1. So this is only one eigenvector in some sense, right? It's got only one eigenvector. So 3 cross 3 matrix with only one eigenvector, and that eigenvector is E1. Okay, so E1 is the only unit eigenvector, and 0 is the only eigenvalue. So in this case, for lambda equal to 0, the algebraic multiplicity is 3, but the geometric multiplicity is 1. There is only one eigenvector.